Hello. Today we're going to discuss differentiability. But first, let's review the intermediate value theorem as stated in the previous lesson. We want to use the following theorem to make a definition. Say that I is a closed interval from a to b and f is a well-defined function. Then the following three statements are equivalent for any point p in the interior of the closed interval. That is, p is between a and b. First, we have the epsilon delta criterion. This states, given a positive epsilon, we can find a positive delta such that, in absolute value, f of x minus L is less than epsilon whenever x minus p is between 0 and delta. Second, we have the topological criterion. This states, for every open neighborhood v sub epsilon of L containing L, there exists an open neighborhood v sub delta of p containing p yet contained in our domain I, such that f of x is an element of v sub epsilon of L whenever x is an element of v sub delta of p and x is different from p. Third, we have the sequential criterion. This says that our sequence f of x sub n tends to L for all sequences x sub n contained in I, where x sub n is different from p and x sub n tends to p. These three statements are equivalent, and if any of these equivalent statements holds true, we'll say that the limit as x tends to p of f of x equals L. Recall that we made the following statement and called it the intermediate value theorem earlier on in the course. Given a closed interval I, let's let f be a continuous function. If L is a real number between f of a and f of b, then there exists a point p in our closed interval such that f of p equals L. That is, f attains all of its intermediate values between f of a and f of b. We found a slightly stronger statement of this using connected sets. Say that S is a connected set. If f is a continuous function, then the image, f of capital S, which is the set of elements y, such that y equals f of x for some x in the connected set S, is also a connected set. We'll use all of this now to define differentiability today. Let's start with the definition that perhaps is familiar to most of you. Say that I is a closed interval and f is a well-defined function on I. Given a point p in the interior of I, that is, p is between a and b, we say that f is differentiable at p if the following limit exists. Here we have the ratio f of x minus f of p divided by x minus p, and we'd like to take the limit as x tends to p. In this case, we'll denote f prime of p as the limit and call this value the derivative of f at p. Here's our first big proposition. If f is differentiable at p, then f is continuous at p. We'll go ahead and present the proof. Let's consider the following three functions on our closed interval I. C, which is a constant function that takes x to the constant f of p. G, which is defined piecewise. First is defined as the ratio f of x minus f of p over x minus p if x is different from p, and f prime of x if x is equal to p. And third, we have a linear function h of x, which is equal to x minus p. We note that all three functions are well defined on the closed interval, and in fact, all three functions are actually continuous at p. This means that the product g of x times h of x is continuous at p, and the sum c of x plus g times h, it must also be continuous at p. But if we take a look at the expression c of x plus g of x times h of x, this is just equal to f of x. But now this proves that f of x must be continuous at p as well. The next big statement that we'll make here involves the sums and products of differentiable functions. Let's say that f and g are both differentiable at p. Then the sum is differentiable at p, and moreover, the derivative f plus g prime is equal to f prime of p plus g prime at p. Similarly, the product f times g is also differentiable at p. However, the derivative of a product is slightly more complicated, and we typically call this the product rule. It says that the derivative of f times g at p is equal to f of p times g prime at p plus f prime of p divided by g of p. As a corollary, all polynomials are differentiable. Of course, we can always form a polynomial inductively by looking at the sums and products of the polynomial x. Let's go ahead and prove the first statement. That is that the sum of differentiable functions is differentiable. Let's say that epsilon is given and positive. We know, since limits exist, that there exists a positive delta such that we have the following inequalities as you see here on your screen. For example, f of x minus f of p divided by x minus p minus f prime of p should be small, as x is very close to p, because again, this is how we define f prime of p. We define it in terms of a limit. Now we'll use the following identity. Here, this considers the ratio f plus g of x minus f plus g of p divided by x minus p. We can now write this ratio essentially as the sum of two different ratios. Using now the triangle inequality, we do see that f plus g of x minus f plus g of p divided by x minus p minus the sum f prime of p plus g prime of p must be less than epsilon. But this is exactly the same as saying that our limit must be f prime at p plus g prime at p. Now let's show the second statement, which is the product rule. Let's say that epsilon positive is given. Since f and g are continuous and I is a compact set, we know that there must exist real numbers capital M and lowercase m such that the absolute value f of x is less than m and the absolute value of g of x is less than capital M for all x in our closed interval I. Moreover, we can find a positive delta such that we have the following inequalities that you see here on your screen. And notice that here we have, for example, epsilon over 4 capital M plus 1 and epsilon over 4 times the absolute value f prime of p plus 1, whenever x minus p is between 0 and delta. Now we use a very clever identity that allows us to consider each of these three inequalities you see at the top of your screen, and we write it so that we have, for example, f of x minus f of p over x minus p minus f prime of p, parentheses, times g of x, plus similar terms. We'll use now the triangle inequality to see that that first sum we just read out must be less than capital M times epsilon divided by 4 capital M plus 1, which of course is less than epsilon over 4. So if we do this for each of the three terms, we then find that our absolute value must be less than epsilon, but this is exactly the same as saying that we know what the limit is. Finally, for today, I'd like to introduce the chain rule. Let's say that f is a function on a domain I, and g is a function on a domain j. We'd like to make sure that the composition G circle F is defined, so we just need to ensure that the image f of I is contained in the domain J. If f is differentiable at P and G is differentiable at L, which equals f of P, then the composition G circle F is differentiable at P as well. Moreover, G circle F prime at P equals G prime at L times F prime at P. Let's explain why this is true. First, let's consider the function capital G on our domain J defined as follows. We'll define it piecewise. First, capital G at Y is equal to lowercase g at Y minus lowercase g at L divided by Y minus L whenever Y is different from L, and is equal to G prime at L if Y equals L. Notice that we can simply multiply both sides to say that lowercase g at Y minus lowercase g at L equals capital G at y times y minus L. We see that this function is actually continuous when y equals L. So now let's substitute y equals f of x. Then we find g lowercase g at f of x minus lowercase g at f of p divided by x minus p is equal to capital G at f of x times f of x minus f of p over x minus p. Finally, since all of these functions are continuous at p, we'll take the limit as x tends to p. On the left-hand side of this expression, we find the definition of the derivative g circle f prime evaluated at p. On the right-hand side, we actually see that this is the product of two limits. First, capital G at f of x, then tends to g prime at capital L. Again, remember how capital G at y was defined, times f prime at p. But of course, this is exactly the formula that we had from before. Thanks very much for watching.